into probability and random variables today, and I have the set of topics right here. Start off with what a random definition of a random variable, discrete and continuous random variables, what they mean, and then what does a distribution mean, what is the cumulative density function, and a very important property of a distribution called the expectation. What is that? Some properties of expectations. And then we'll go into some discrete distributions, Bernoulli, binomial, and Poisson. And then next time we'll go into continuous distributions, Gaussian, exponential, and power law. Okay. So far, what we've been talking about in terms of probability is very limited, very to events and observations. So we have things like an event, like a die coming up or something like that, or an observation of that event. But these are, in some sense, elementary things. We want to do something a bit more sophisticated, and what we do is we introduce this notion of what's called a random variable. And let me kind of introduce that through an example. Let's say that I toss a die, and the die comes up, and the face it says 1, and then toss it again, it comes up with a 3, and now I have these two observations, die coming up 1, die coming up 3, and I want to actually do the following. I want to look at the probability that the sum of the die's values is 4. Okay, so the sum of these two values is neither an event by itself nor an observation by itself. It's a sum. Okay, it's something that can be derived from the underlying observations, but it's not the event or observation itself. So it's convenient for us, but it's random, right? We don't know the outcome. So if I toss the die 2 times, the sum is not. It's sort of a compound which has some probability associated with it, but it is not an elementary event or observation. So a random variable is something like that. It is a variable that has some probability associated over some domain. So we have a domain. What we call the domain is a set of underlying events, and what we do is a random variable assumes a particular probability for each element in the domain. So that is what we mean by random variable. So more precisely, so you can define a random variable to be a real valued function over its domain. Okay, so if you're going to throw the die 2 times, well, all the possible values are basically between 2 and 12, right? You can never get anything smaller than 2. You can never get larger than anything than 12. So we can look at now the probability that the random variable, that is the sum, assumes a value of 2, of 3, of 4, etc., all the way up to 12. And so we can see that the domain in this case is 2, 3 up to 12. And then we have some probability. We can define the random variable r, for example, and we can see the probability that r equals 2, or the probability that r equals 4, which is what you talked about earlier. So here, right away, you can see that the value r is not an event or an observation, it's a random variable. So it's fundamental concept. You need to understand a random variable is like a variable in computer science. In a program you have variable, except that the value takes on is not deterministic, it's probabilistic, and the probabilities are defined over elements of the domain. Okay? So any questions about this so far? So we've probably all seen random variables before, and you have to sort of go back and remember what a random variable is. And once you know what a random variable is, then you can start discussing about what is the probability it takes any value in its domain, right? But we need to kind of go back and remember what a random variable is. All right. So that's just get you started. So the two kinds of random variables, which are the discrete and the continuous, depending on the domain. Okay, so a discrete random variable is very simple. The domain is discrete. Which means we can enumerate the entities. You can enumerate it. It doesn't mean it's finite. It just means it's it can be infinite. It's just enumerable. So it can be the irrationals, for example, or integers, which are infinite but enumerable. And we require that the elements of the domain the elements of the domain have to be mutually exclusive and also exhaustive. What this means is that if I enumerate the entire domain, if I say this is what the domain is, then one of the elements in the domain has got to happen. Okay, I mean, in other words, we can't say, well, it didn't happen at all. In other words, going back to the axioms, the probability associated with the entire set of the domain is going to be 1. Okay, otherwise it violates the axiom. So we need to kind of enumerate all possible outcomes, okay, in some fashion. And secondly, you can't have two happening at the same time. Okay, these are mutually exhaustive. Okay, so we can say a random variable over here assumes a value 2, or it assumes a value 3 or 4 or whatever, but it can't assume 2 and 4 at the same time. Okay, and again, it's sort of a fairly obvious and a logical thing. So when you enumerate the domain, you got to make sure that you aren't, two elements cannot happen at the same time. Okay, that's just a straightforward thing. In this case, then we can very naturally associate a particular probability with each element in the domain, and we have the natural condition that the sum of these probabilities needs to be 1 because something in the because the domain is exhaustive. So to give an example of this, we know that the IP header in a packet, the IP header is 16 bits. So the largest IP packet is 64 kilobytes. So what that means is that if I take the random variable, which is the IP packet length rounded up to the nearest kilobyte, it has to take values ranging from 1 all the way to 64. It can't be anything larger than 64 kilobytes. So here, this set, 1, 2, 3, etc., the integers up to 64, represents the random variable packet length rounded up to nearest kilobyte, and it's mutually exclusive because a packet can't have a length of 1 and a length of 2 at the same time, for example, and it's exhaustive because all packet lengths must be in this particular range. The people who are in that corner over there, you might want to move here because otherwise when I write over here, you won't be able to see it. So there's enough space for maybe 3 people over there, so maybe you want to do that. Okay, and yeah, and okay. Okay, while they're doing this, any questions about this? Again, this is pretty basic stuff. Okay, 2 people. There's one person can squeeze in there if you want to. Indicate can you see everything? Or there's some chairs here. You don't need to bring a chair even. There's 2 chairs over here, so a couple of people can squeeze in here. There's 1 space over there, I think. Okay. All right, and I'm sending around this sign-up sheet so that I have, just pass it around. Maybe we should recirculate it for people who came in later, and I'll get some idea of how many people are there. I thought there's 37, but maybe there's more than 37.
I think it's growing.
It's growing. Okay. So some of you should just watch it on the web. And after all, we're being videotaped. Okay. So that's a discrete random variable. Pretty straightforward. So what's a continuous random variable? Again, it's no big deal. Continuous random variable means that the domain is continuous. So we can think of the continuous random variable being a subset of the real line. It does, that's good enough for us. In other words, we take some interval, and we say basically that's a real line, and you have points, you have an infinity of points in a real line, and we associate that this can be associated with any continuous domain, by obvious translations. So we can just say the domain is such as a real line. And we now have this notion of, so we can just say that at each point we have some kind of probability. And I'm going to be a little bit vague about what the probability means just for now, and in about 2 minutes I'll explain what that means. But all I want you to understand, in the continuous random variable case, the domain is a subset of the real line. Typical example of continuous random variable, and something that you'll see all the time in queuing theory, is time. Okay, because time is continuous, it has a one-to-one mapping with the real line. So you can say the time between two arrivals of packet to a particular switch is a continuous random variable, because it takes a value which is from the subset of the real line. So immediately when you say time, unless you quantize time, which is quite often done for reasons of expediency, and but unless you do that, time is your kind of prototypical continuous random variable. Okay. Now, I mean, there is a philosophical argument that, even time is quantized. Any event that's shorter than some very, very small time duration can be thought to be in some quantum thing. And similarly, of course, anything in space is quantized by the Planck distance or something like that, so 10 to the minus 33 centimeters. So, well, the whole world is discrete, but I'm not going to argue that. It's another, you have to have a lot of beer before you argue that. It's too early in the day. So we'll think about it as infinitely subdividable, etc. So it's a continuous random variable. So immediately we come to the problem of what is the meaning of probability for a continuous random variable. And perhaps the easiest way to do it is to first look at the discrete case. So in the case of a discrete case, with each element over here, I can introduce a probability. Let's say x has domain, okay, over here. So instead of say x equals, it should say domain of x. Let's say domain of x is the set 1 to 64. Then we can have this value probability x equals 1, for instance. That's a probability. And now I can give you the value, if you will, like a histogram that tells you the value of the probability that x takes on each of these values. And we call this the probability mass function. Mass function. And of course, we can express that in the form of a set as well. So for example, if you take the die, we can have the following set, 1 over 6, 1 over 6, etc. The 6 elements over here is the probability mass function. And if you like to think in graphs, then what we can do is we can say this is the probability mass function. That's 1 over 6. That's probability mass function for the die. We can similarly think of the packet length for IP to have some other probability mass function. Maybe many packets are small. There are very, very few intermediate packets. And then there are some large packets like this. Okay, so what do we have to make sure? That the total values across that histogram add up to 1. And that is a probability mass function for the discrete random variable. Again, very straightforward. We just take the random variable. Random variable has a domain. For each value in the domain, we tell you what the probability of that particular thing is. And now we know why it has to be exhaustive, because the sum of these things has got to add up to 1, which means we know for sure that something in the domain happened. Okay, that is what we mean from Kolmogorow's first axiom. First or second? Yeah, the first, one of the axioms. Okay. What about continuous? Continuous actually is where students start getting really confused. Because I have let's say I have this thing over here, and I'm going to now start defining what is the probability associated with any point in this particular space, in this line. It turns out the probability of any element on this line is 0. We already talked about this, right? And if I take any particular element like 0, let's say this is 0 and this is 1, and I say this is 0.5, the probability of any particular element actually is 0. Okay, so what does it mean? Okay, what is it? How can you even associate probabilities with this? So there are a couple of different ways of thinking about it which will make sense. So one way of making sense of this is that let's say that we take two values x1 and x2 that are in the range 0 to 1. Then what we can say is that probability that the random variable x, okay, is probability that x1 is less than equal to x less than equal to x2 is given by the integral from x1 to x2, these p x dx. Let me make sure I use this. Yeah, I'm using small p, so px dx. So in other words, I'm associating with this domain over here the density function px. This is a density function, not a mass function. This is a density function. Okay. In the discrete case, we have the probability mass function. In case of a continuous random variable, you have a density function, and the density function really says this amount of probability that x takes on a value in this particular range. Okay. And what we can do is we can make this as small as we want. We can say that the probability of x, of the value x, in some sense is, you can think of it as when x2 is close to x1. Or you can say x2 equals x1 plus delta x. So that's sort of this very, very small thing. So we can think of the a limiting process where we make this smaller and smaller. Of course, if we make it too small, then we'll have 0, because any point is going to have 0. But we can have this sort of intuitive understanding that the likely points, okay, probable points or highly probable points in this distribution are going to be having larger values as you make delta x small. And so we can actually draw something like this. We can have, let's say, this is the domain. In this case, it's an infinite domain. And I can sort of draw this curve like so. And of course, this curve has to be below 1, because what we're requiring is that, obviously, minus infinity to infinity px dx equals 1. Okay? So over the entire real line, we must make sure, no matter what the continuous function is, so no matter what the probability function is, it has to be the case that over the entire real line, the probability adds up to 1. Now, of course, it may be 0 for very large portions of it, and it may be only defined in a subinterval like 0, 1, but that doesn't matter. This equation is going to be true always, right? So if I draw this curve over here and I choose some value over here, that's x, okay, I can define, in this case, a density over here. The px is actually defined as a point over here, but it has to be interpreted in this somewhat funny way that, I'm going to take this function and I'm going to take this value x1, x2, or x plus delta x, and then the area under this curve over here, okay, is the probability that I'm going to have this particular value x. And this is where it gets confusing, because you obviously say, well, if I take this point and read off the value over here, that is the probability of that point. It sounds correct, it's not correct, because the probability of any specific point is, again, is always going to be 0, because there's infinity of points, etc. So this, we can only view this in the limiting sense of what happens in the range x to x plus delta x. Okay? And in some sense, what is the area over here? Okay, again, even the reason I'm saying the probability of 0 is when you take delta x to be 0, then you have a straight line. The straight line has an area of 0. So the probability of the point is 0. Right? We can only kind of look at this area over here versus this area over here, and for the same value of delta x, we can say, well, this is larger than this. So this area is sort of more probable than that area over there. Okay? But that's where things start getting kind of confusing, because we're looking at limiting values of areas where the limit is actually 0. For every point, the limit is 0. However, when you make it non-zero, slightly non-zero, then you get a larger rectangle here than over here, and so this becomes a little bit more probable. Okay? And we can imagine physical processes that give rise to these and many. But for example, if I take this chalk and I drop it on the floor, well, it's going to bounce. Okay? Now what I can do is I can sort of draw these rings of probability from the point directly above where I toss it, and you can obviously see that it's more probable to be here than to be at the other end of the room. So we can draw, in some sense, if this is a center point, I can draw this fairly sharp decline in probability, like so. Right, and then what's going on is that it's likely to be towards near where I dropped it. That's what this graph is showing me. Okay, and of course I'm drawing this in one dimension. You can have a similar two-dimensional density function, which is the obvious extension of this. But nevertheless, the point is that it's more probable over here. But any specific point is going to land there. The value of there is 0. Okay, so we can talk about regions which have higher probability and lower probability, but any specific point is 0. Okay, so this is how we get around that, and this is something you really need to kind of internalize, that the density function for a continuous random variable is giving you sort of a sense of what it is in the neighborhood of that point, rather than any specific point itself. Okay, and as long as you kind of remember this integral over here, that's really what it comes down to at the end. Okay. Let me stop here. Are there any questions about this? Anybody? Yeah.
Is it necessary that all the values of the curve be less than 1?
Is it necessary that all values of the curve be less than 1? Well, what is necessary is that the area under the curve has to be less than 1. So yeah, you could have sort of a very, very sharp spike going up and coming down or something like that. But we need to make sure that the area under the curve has to be less than 1, right? Has to be equal to 1 actually. So can we have that? I've never seen a continuous thing with the sort of spike in the but you can have it, yeah. Right. Okay, yeah, that's true. Yeah, so this, you're right. So maybe I should take that out. That is not a requirement. The only requirement really is this over here. Yeah. Okay. Yeah, sorry. That's a good point. So you should. Most nice functions stay below 1, but yes, I think you're right. Exponential will actually can have a higher value. But we'll come to that next time, next class. Okay. So that is the density function. Let me just talk about one more thing, the cumulative density function, and then we'll take a break. So let me, I'll just erase everything over here. Now for the, okay. So the CDF can be thought of as cumulative density function or cumulative distribution function. For discrete random variables, we have to assume that the domain is ordered, okay? Because earlier I just said the domain is some set of values over here, but now what I'm going to do is I'm going to impose ordering restriction. That means that any two values, one is greater than the other. If you take two values D1 and D2, either D1 is greater than D2 or D2 is greater than D1, in which case we have a total ordering. Okay, so we take the total ordering and we just impose it and we have some ordering. Then what we can do is we can say what is the probability that the random variable takes a value less than certain value D1 or D2. So let's take an example again. Over here, let's say the values are integers 1, 2, 3, 4, 5, 6. This is clearly a total ordering. I can now compute what is, and let's say this is x is defined by this. What is the probability that x is less than or equal to 3? This is nothing more than p x equals 1 plus p x equals 2 plus p x equals 3. Now, why can I add them? Okay, why can I add these? Because they're mutually exclusive. These are mutually exclusive, so obviously I can add them. And so generally speaking, I can define sort of the CDF of x, okay, CDF of some value d is basically the sum that d less than equal to di less than equal to d, p of or px equals di. Okay, so the CDF at the value d, so the cumulative density function at the value d is just you sum all the points less than d in the total ordering, you just sum the probabilities. So this is just the example, that's the more general definition, and I hope I'm using the same. Yeah, so, yeah, well, or what I've expressed in the, we call that the f of d equals sigma I such that d sub I is less than d, p di less than equal to d, sorry. Okay, so that's a cumulative density function, and let's say x has this domain and it has the value 1 over 6, 1 over 6, etc. Then the CDF, the capital F of D, which is the is just nothing more than 1 over 6, 2 over 6, 3 over 6, etc. 1. And as you can see, the last value for any distribution is going to be 1. Right? CDF has got to be 1. That is obvious. And so we have that. The analogy for a continuous process is pretty straightforward. What's the analogy over there? We just say that if we have something, so we have, let me just make sure I'm using the right notation over here. So, right, so we define the f of x as the cumulative density function for a continuous random variable is just integral minus infinity to x px dx. So again, the interpretation is straightforward. I have some continuous random variable. It has some domain. It doesn't really matter what the domain is, but we know that going from minus infinity to x, we have these, this is the amount of probability that it's less than this. Now, actually, all this is one-dimensional. You can think of, multi-dimensional extensions. They all follow the same form. We just have to define the ordering the right way. But in this case, anyway, we have a pretty straightforward understanding of what a cumulative density function is for a continuous random variable. It's a probability that the value is less than x. Now, unlike the density function, which we run into problems for a particular value x, we don't know what it means. What is the density function at x? It's kind of this vague thing. The cumulative for a continuous random variable is pretty well defined, because it's an integral already. It's integral from minus infinity to this. So in many cases, we prefer to work with cumulatives for density, for continuous variables rather than the density functions. Okay, it just is a little bit easier to work with. We're not dealing with these vague quantities. Okay, the cumulative is very, very well defined, and so we kind of use that. Okay, just to give you an example of this, we can take the following continuous random variable, and here's the continuous random variable. It's defined on the domain 0 to 1, and it's 1. The value is 1 over this whole interval, and then it's 0 elsewhere. All right, so what is the area under this curve? The area under this curve is 1. Right, because it's a unit square. My square is kind of skewed. Maybe I should make it more square. That looks more like it. There. So we have a nice square. So that's a unit square. And so this is so we define this as px equals 1 for 0 less than equal to x less than equal to 1 and 0 otherwise. Okay, this is where I said people get confused. They're saying, oh, the probability of any particular value here is 1. That means it surely happens. Right? No, it doesn't. It surely doesn't happen. It surely, in fact, as I said, almost surely doesn't happen. Even though the density function of this is 1, right? It actually doesn't mean anything because the probability of any particular value is 0. Okay, so this is where kind of intuition and math collide and math wins. Okay, intuition loses. right? Math wins, because I'm saying over here, let's take this value 0.5, p of 0.5, well, it's equal to 1. P of 0.25 is also equal to 1. If you use the discrete random variables, this is like, oh, so p 0.5 plus p 0.25 is 2. What happened here? Well, it is 2, but at the same time, this is not true. The value of the function is the value of the value of the density function, okay, is in fact this. So we basically say f of 0.5 is equal to 1, but the probability that x equals 0.5 is equal to 0. Okay? So the density function f, which is actually what I'm drawing over here, and the cumulative, of course, is capital F, is what I'm drawing over here has a value 1, but the probability is 0. Okay? Because it's not, the density function is not the probability. If all you remember from this lecture is this one fact, okay, you're already way ahead of many other people. Okay, who, I should say, many other grad students joining the department here who look at this and say, oh yeah, the probability of this is 1. Like, yeah, right, okay. Okay, so what about the cumulative density function? Well, the cumulative density function of this same thing is nothing more than, so f of x is equal to integral minus infinity to x, fx dx, which is equal to minus infinity to x 1 dx, right? Because it's fx, okay, and this is nothing more than x, right? Just by integrating 1, you get x. So what is that? It means that in the range 0 to 1, it is 1. And then, actually, it's not even defined beyond this range 0 to 1, and it goes up straight like a line. So, and of course, it reaches 1 at this point over here. At 1, it reaches 1 because it's x. So this is nothing more than our old friend, the uniform random variable, okay? Because the probability of any particular value is, it has, all of them are equiprobable, and the cumulative probability of getting any value over here is in fact the value x. So the probability that the variable is less than or equal to 0.9 is equal to 0.9, for example. Okay, that's the definition of a uniform random variable over here. Okay, so so a grad student came to me some years back, you know who you are, and I said, okay, you ran the simulation. Yeah, I said, what random variable did you choose? He said, I used random. I said, okay, random is fine, but what's the distribution of the random variable? And he said, well, it's random. So people think if you call rand, that's a random variable. What is the distribution? Who cares? This is computer science. In reality, what you get back from rand is p. Basically, what you get is uniform random variable. And as we'll see, this is not the end of the world. There are other distributions as well. Okay. All right. Any questions on this so far? Yeah.
The domain of a discrete random variable is not necessarily bounded, right?
Okay. What's the question? Say that again. The what is not? The domain. Domain is not bounded. That's right. The domain is.
So we can consider discrete random variable in which the domain is the whole positive integers.
Yeah. Sure. Sure.
So the probability of each point should be 0.
No. So the question is, if the domain of a discrete random variable is infinite, how can we make sure, aren't the probability values 0? Well, it's not the case. Let's take the standard series half, 1 over 4, 1 over 8, etc. Okay, 1 over 2 to the n. So the sum of all this is equal to 1, right? It's an infinite sum, right? So each value of this, I can say, is non-zero, because 1 over 2 to the n, 1 over 2 to the n is not 0. It may be very, 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 very small, but it's not 0. It could be 1 to 10 to the power, 10 to the minus 1,000 or whatever. So it's very, 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 very small, but it's not 0. In fact, it's never 0, right? It's never 0. So that's a domain. It's enumerable. I can enumerate it. And the probability values that I'm putting over here are enumerable, and the sum actually sums to 1. right? In the limit, it sums to 1. So this is an example of an infinite domain where where things hold, but none of the values are 0. Right? But there are many others, by the way. This is just the simplest one, but there are many, many others. Essentially, any series, okay, any series that sums to 1, and there's many of those, are valid probability mass functions for a discrete random variable. To give a very trivial example, I can also have half, 0, 1/4, 0, etc. That's another series that sums to 1. So I can put all sorts of zeros there and still get the same sum. So that gives me a kind of a cheating way to give you infinite number of distributions which all have sums to 1 without doing any work. So
Cannot be kinds of uniform.
it cannot be well, it cannot be uniform. That's true. It cannot be uniform, but it can be, yeah. Any other questions? Yes.
So how do you actually get the probability density function itself? I mean, the probabilities are all such ratio, right?
Right. So the question is, how do you find the probability density function for a continuous random variable? So there are two approaches. One approach is analytical. Okay, we'll see that certain events, especially events relating to time, it's possible for us to write down the cumulative density function, and then differentiate it, you get the density function. So as I said, it's much easier to work with the cumulative. So we can write down the cumulative and then differentiate it. The other way of doing it is to think of the density function as being the limiting value of a histogram, where the bins are getting smaller and smaller and smaller, right? So delta x is nothing more than the bin size. So I can essentially take a discrete distribution and make the bins smaller and smaller. And at some point, I can say, well, I'm going to approximate to the continuous because there's just too many bins. I have 1 million bins, and they're all very, very small. Let's call it a continuous density function. So empirically, or from a frequentist approach, you can come up with the density function in this way. It is an approximate, right? Analytically, of course, it's not approximate. Analytically, we can come up with the functions. When you talk about the Poisson, especially when you do queuing theory, look at birth processes, you'll see that we can come up with analytical ways of describing interarrival processes, which are in fact continuous and have a density function. So one more question somewhere else. Yes?
We can also consider something like a hybrid of continuous and discrete distribution. For example, with 1/2 a random variable takes value 2, and with 1/2 it's uniform in 0 to 1.
Yeah, so the question is, can we have a continuous, can we have a hybrid of discrete and continuous random variables? Yeah, I suppose so. I mean, again, it can be thought of as a function that looks something like this. For example, we could have half, so in the 0, 1, and then at the value 0.5, it has a probability half. So the total probability under is equal to 1. So I mean, these are all sort of pathological cases. I've never seen something like this. I don't know why you would want such a thing, but yeah, maybe it's useful. Yeah.
It's called a Dirac delta function.
Okay. Yeah. Okay. Yeah, I know that this is the Dirac delta. So, but why do you want a Dirac delta in a probability?
So he wants a continuous random variable with 1 point, a
Yeah.
discrete point having
Yes.
finite probability.
Yes.
There you just put a Dirac delta with
Yes.
and weight it to the probability that you want.
Right.
So when you take the integral over
Sure. Yeah. No, I agree with you that you can do it. I mean, it's not impossible to do. It's just that I don't see why. I mean, you can dye your hair pink and walk around naked. I mean, it's improbable. You can do it, but why would you want to do it?
A concrete example of that could be the waiting time distribution, for example, in a queuing system. It can be 0
Yeah.
if the system size distribution is 0
Okay.
when a job arrives, and if there are some other jobs
Yeah.
at
Yeah.
the instant of arrival, it follows a continuous distribution. So it has a jump at 0, and then
Yeah, jump at 0 I can believe, because you want to have some mass at 0, or actually we also have, in the case of histograms, we have this sort of greater than something x. So you have something like this and you say, okay, at the end I want all the remaining values to be captured with the jump, because that's all the stuff I don't care about. But in the middle, no, I don't know why you would do that. But anyway, we're getting far ahead of ourselves. I just want to give you this main idea, which is that the probability of any particular point, even though it's 1, is not surety. Okay, so let's stop here, and we'll continue with expectations, I guess. Okay. Probability. So we have this, the probability density function as I said, is some function. It doesn't really have to be anything. As long as the area is below 1, area adds up to 1, I'm sorry, it's fine. So one, when we study statistics, we'll realize that a distribution or a density function can be characterized in very many different ways. But for now, we're just going to look at a simple representative of a distribution, which is called the expectation. And this is a very important, from the perspective of probability, this is a very important property of the distribution, discrete or continuous. And what it is that if I tell you if I tell you this is a random variable that represents some quantity, and I don't know anything else about it, I don't know any conditions, I don't know anything, I just think this is a random variable, this is its density function, what value do you expect it to take? Okay, that is the intuitive meaning of expectation. So knowing nothing more about it, what's the value you expect it to take? For instance, okay, I'm going to give you an example over here. Let's say that on this axis I have time, and on this axis I have the maximum daily temperature. And I'm going to make the, I'm just going to make it continuous because it's easier to draw. Of course, I should make it discrete. But let's just make it continuous for now. And the maximum daily temperature around here is, this is 0. So let's say it's minus 30. So the maximum sometimes is minus 20. Anyway, so this is January, whatever. This is a reasonable graph of the maximum daily temperature, and I can normalize it so that the area under this graph is 1. So we can think of, so this is time. Actually, I need to kind of change it to have the, okay. So this is time and temperature. Now what I'm going to do is I'm going to flip the axis around, and I'm going to have on the x-axis I should probably draw this as time. Right? Now I'm going to change it around, and here I'm going to have temperature, and here I'm going to have probability of temperature. So now temperature is my random variable. I'm looking at probability, and basically, we kind of have very few low temperatures, very few high temperatures, and sort of something like that. And then, maybe it doesn't go below minus 30, it doesn't go above plus 40. And this is perhaps the density function of temperature, right? So remember, there are two different graphs. This is time and temperature. So this is what the weather office produces. And then I kind of massage the data, and I get this one. This is the density function. Now somebody is coming to visit you from wherever, and they don't know anything about the time of the year. They don't know anything about the density function. And what temperature do they expect for that day, right? Just randomly chosen day. What temperature do you expect? They basically expect, if this is called temp, then E of temp is the expectation of the maximum daily temperature for a randomly selected day. That's what I mean by expectation. So of course I can condition, I can say, no, today is January so and so. Then of course you can look at the distribution for January, only January, so January 10th. But if I don't know anything more about it, I just say this is the density function, you can compute the expectation, and that gives you sort of a rough idea of what the expectation is. Or another example of this could be that, you have a bus schedule. The bus is supposed to come at 3 o'clock, but in fact, it has a distribution around it. And we can look at the probability that it comes at 3 and 3:01 and 3:02 and 3:03. We find the mean of this, and that is the expected value of the bus arrival time. Okay, that is your expectation again. So expectation has some good intuitive properties. What I'm going to focus on next is how do you compute it? Or actually, it's just defined something like, so the expectation of a discrete random variable D is defined to be nothing more than, so we take the sum over the entire domain, the value of the actual value times P of DI, right? So, I'll do an example in just a minute, but this is an example of, this is definitions. We just multiply the domain value with the probability of the domain value. And in a similar value for a continuous domain, it's nothing more than an integral from minus infinity to infinity, x px dx. Right? We're just multiplying the value that it takes with the probability, the density. It's not the probability, but the density. And we take the integral, and that's the expected value of a continuous distribution. So let's do a couple of examples to make these a bit more clear. So what I'm going to do is that, let's say that I have this domain. I'm going to use this from the notes because then I don't need to do the math again. Let's see. Where did I put it? Sample 10. So I have a variable d that takes the values 1, 2, 3, 4, or 5. And the probability it takes the value of this is going to be 0.2, 0.3, 0.2, 0.1, 0.2, 0.2, 0.3, which sums up to 1. Okay, that's why I just picked those numbers, sum up to 1. And so I can compute the expectation of d as just 1 times 0.2 plus this one 2 times 0.1 plus 3 times 0.2 plus 4 times 0.2 plus 5 times 0.3. Okay? That's the definition. You take the value di multiplied with pdi. So this is pdi. And you just multiply it. And this turns out to be, I guess, 3.3. Yeah, 3.3. So, two observations. First observation is trivial, which is, this is pretty easy to do, it's not a big deal. The second observation is non-trivial, which is that the expected value of d is 3.3. However, it's not one of the values in the domain. Okay? For a discrete random variable, the expected value can be something that actually is impossible. So it's kind of crazy, okay? I'm saying these are the values in the domain, and the expected value comes out to be something you can't even have. So intuitively you can say, well, what this means is it's like 3 or 4. You just kind of go the closest two values and say, well, 3 and 4 are both likely. Okay, it's more likely to be 3 than 4 because it's closer to 3 than 4. But we can have these sort of counterintuitive situations, which is why I actually picked this example, because I wanted to show that. Okay, any questions about this? So expectations are fine, but be careful because the expectation may be unrealistic, maybe impossible actually. Second thing we'll pick is the domain is the interval 0, 1, and we'll have px equals 1 in the domain. This is your uniform function, and so we can compute the expected value. So the c has a, so expected value of c is nothing more than integral minus infinity to infinity, which is what we did, x, px, dx. This is what? Just px is 1, so integral minus infinity to, oh sorry, it's a 0 to 1 because it's not defined outside the range. It's 0 to 1, x dx, which is x squared by 2, 0, 1, which is half. Okay? That's just simple math. So the expected value of a uniform distribution is its midpoint, half. Okay, and we can take any two values, x1 and x2. You'll see right away that it's going to be essentially the midpoint of the range. It'll just kind of pop out that way. All right, so that's the expected value computation. You can see that all we really need to do is to kind of formulate this and integrate it in the domain of definition. In this case, it's defined over this range 0, 1, and we get the expectation. So the expected value of a uniform random variable is in a 0, 1 uniform random variable is 0.5, and you can figure out if you change the domains what it's going to be. Okay, any questions about this here? Okay, so let me take a few minutes, and then we'll talk about some properties of expectations, and then we can take a break at that point. All right. So what are the properties of expectations? So these are, I'm going to state without proof. These can be proved. And the way you prove it is basically to unpack the expectation in terms of its definition, and then you do the whatever math is needed, and you pop it out, and you get back the properties. So first property, and these are really worth remembering because you'll see them over and over again. It's very useful. So for constants A and B, the expected value of A times X plus B is A times, X is a random variable, A times expected value of X plus B. Okay. So what we're saying is we can take the X value, put it through a affine or linear transform AX plus B, and we can just move the constants out. You can just move the E into the X, and we get AEX plus B. Okay. This is a very useful property in some cases. The second one, and I'll do this, I'm going to change the order slightly from what's in the notes. The expected value of X plus Y. So if you take two random variables X and Y, and we want to know what's the expected value of the sum, okay? It turns out that you can easily show that this is nothing more than expected value of X plus expected value of Y. And more generally, the expected value of the sum X sub I is nothing more than the sum of the expected value of the Xi's. In other words, if you want the expected value of a sum of random variables, we just take the sum of the expected value of each one. Now, I never said anything about independence. These random variables may be dependent, may be independent. We don't care. We can just use this result anyway. It works whether they're independent or not. So this is just a kind of this is a nice thing to have when we start looking at larger systems. And the third property is even nicer. It says expected value of f of x, where f is any function, is nothing more than the f of e of x. Sorry. Oops. Okay, so we can take, what we can say is that, from a symbolic manipulation purpose, we can pull the f out of the e. If you have an e of f of x, we can make the f of e of x. And that again, of course, it goes both ways. So we can, if you have f of e of x, we can kind of pull this out. So what this means is we typically have these large expressions, okay, which have many, many terms in them, and we want to find the expected value. We can start using these terms. You can pull the f out, and then maybe this one inside has got sum, so you can pull the sum out, etc. And then for each smallish one, we can find the expectation separately, and then put it back together again. So this is sort of a process by which we can unpack and pack things together. So these are some properties, and to give you an example of how this is used, let me show you a proof over here. Yeah.
Does f have to be linear, or, I mean, like ex squared is clearly not equal to x. Like if the expectation of x squared is not equal to the square of ex.
Is it linear? Okay, I have to go. Yeah, I think. Okay, let me figure out. It may be a bit strong. This may be too strong. I'm. Let me check. Or does somebody else have the definitive answer? It has to be linear. Especially linear. Yeah, that sounds. I mean, I think. Okay, I'll check this. Okay. Yeah.
If you write the right hand side in terms of the integral,
Yeah.
it's correct. E of fx, e fx equals to integral of fx.
Right.
Fx and this function of x.
Mm-hmm. So you're saying I can write this as f of.
Correct. F is linear, but if you want to.
Yeah, I see what you mean. Yeah, we need to move it into the integral. It has to be linear. Yeah. Okay. So I take it back. Sorry. I should have said any linear function. But I'll check anyway. There may be something which may be better than linear. Right. Yeah, that's right. You're right. Jensen's would actually. Yeah. So this is any linear. Okay. But I think we may actually be able to do something stronger than linear, perhaps. I'll check and see. let me make a note here. Okay. Sorry about that. Clearly I slipped there. I know it won't work for something strong. Okay, it won't work for some things, but it might work for something beyond linear. So in the next class, I'll tell you exactly what that is. But before I do that, let me. Yeah, sorry. Here questions? Yeah.
If you write it like this, it must be correct.
Yeah. I understand it will work for linear. I'm just saying, is there something stronger than linear that I can use it for, right? Maybe there's something even more powerful than linear, but linear is a sub part of it. So I just want to be very precise before I tell you this is. The linear is okay, but I want to go beyond linear if possible. Any other questions? Okay. So I want to show you the variance of a variable. Variance of a random variable x. Okay, it's defined to be, so the way that it's defined is a bit interesting. It's called v of x, and it's nothing more than the expected value of x minus e of x. Okay, but the square isn't exponent. Yeah. So what we're doing is this: we have some random variable x. It has some values. It's discrete or continuous. We don't care. It has some expected value. We can think of it as the mean. This is the difference, and it can be positive or negative. X minus e of x can be positive or negative, and the square is always positive. Okay, so that's how we square it. And what we're saying over here is that we want to find the expected value of this sum of these squares. Okay. So what's going on is that, if you have some distribution like this, and we have some mean over here, so these are the areas that are above and below in some sense, and we're taking the square so that it's always positive. So the square over here is perhaps something like this, and it always goes up. And then what we're trying to find out is the expected value of this square, which would perhaps be something over here, and this gives us a measure of the variability of that function. And why does it give a measure of variability? Because if you have something that's variable a lot, then the expected value is is a constant, where this function varies a lot. And because it varies a lot, the gap between x and its expected value will be large. If that's large, the square is large, and then the variance will be large. So intuitively, if the variance is small, we have a function that's not moving around too much. It stays near its mean. So again, if you're taking some function which looks like this, it's going to have low variance, and this will have a high variance. So it's a mathematical quantification of the amount of variability in some function. In this case, we're looking at the amount of variability in the density function, okay, of x. Okay. So now, how do you compute this? It turns out there's a very nice way of computing it, which is that v of x is nothing more than e of x square minus e of x square. Okay. So what we do is that we have the expectation of the square minus the square of the expectation. So this is the equality, and I'm going to show you how you can prove it using actually just the first two things. Okay. Okay. So this is useful when you run simulations. If you're running simulations, often you have some variable, and you can think of it as a random variable, and we want to compute both its mean and its standard deviation or variance. Okay. What we do is we just keep track of just two values for that variable. Let's say the variable is v, then we'll just have two program variables. One we call v mean, and we can another thing called v mean square. Okay, or whatever you want to call it. Basically, every time the value v changes, you add it to v mean, and you increment some contour. So you have n. So you increment the number of you increment the number n, you increment this, and you square the variable, and you add it to this. All right. At the end of the simulation, if you divide this by this, you get ex, And if you use this formula, you can get the variance. So you just need 3 variables: the counter, the sum of the values of v. This is just sigma v, and this is sigma v squared. And we can actually compute based on these, and this inequality, you can compute the variance of v. So it's quite useful when you're doing simulations. It reduces the amount of work, and also you're doing a little bit of work at each step instead of a lot of computation at the end. So this is a trick you use. Anyway, to get back to this, how do we prove this? Well, we'll just expand this out over here. So this is E of, this is x squared plus 2x E x plus EX squared. Okay, it's the expectation of the whole thing. And if I expand this, this is E of x squared plus 2, I take the constant out, E of x EX, oh sorry, minus 2 plus EX squared, right? This is just expanding out this term by term, because I can, using this rule over here, E of x plus y, so it's the expectation of 3 things, so I can kind of unpack it this way. Now, this one is E of x squared, I'll just leave it like that. Now, if you look at this, E of x itself is a constant, right? E of x is just a constant because it's the expected value. So the expected value of this can be pulled out, and we get essentially minus 2 times E of x plus E of x squared. And of course, these two cancel out, so I get what I wanted, E of x squared minus E of x squared. Okay, so the trick here is that the expectation of, inside the expectation, that's just a constant. And then you pull it out, you get E of x, it's of course E of x the whole squared, which is the same as that. And so we get this result in just 2 lines, 3 lines of derivation. And as I said, that's a very useful result to have. And all of this comes out just by using these first 2 rules. Constants, you can pull out constants, and secondly, you can move the expectation into a sum. Yeah?
Prof, from this result, we can actually conclude that the expectation of x squared is not equal to...
Yeah. That's true, yes. Yes, so thank you. I'll come back to what f is in a bit. But yes, clearly that is not true for quadratic, but I want to be stronger than linear if I can. Okay, maybe linear is best you can get, but yeah. Any other questions about this over here? Okay, so let's take a short break, I guess, and I'm way slow. I have to go faster. Oh gosh. Okay, let's take a... I thought I'd be done with this a long time ago. Okay. Common discrete distribution. So there are some distributions that show up all the time. It's useful to know what they are. And I'm going to see if we can get through all 3, but maybe I have to stop. But anyway, so the first one is Bernoulli. And Bernoulli is the easiest one. Bernoulli is a discrete variable, which means that the domain is just 2 things, and it's represented 0 or 1, or success, failure. I should use sets properly instead of this. And well, the random variable has either succeeds or fails, and it has probability p of success. So x, probability that x equals 1 is equal to p, and the probability that x equals 0 is 1 minus p. It's often called q in the literature. So that's it. So you do an experiment, whether you succeed or you fail. So there are 2 possibilities in the domain, and we give p is the parameter for the Bernoulli distribution. And well, that's basically all there is to it. There's nothing more to be said. It's straightforward. Okay, so however, Bernoulli gives us the basis for a more interesting distribution called the binomial. So what a binomial is a sequence of Bernoulli trials. Okay, so we have an experiment. It can be success or failure, but you're going to do it many times. You're going to success, failure, success or failure, success or failure. And what we want to know is how many successes did we have, right? So kind of a normal thing to expect. So to illustrate this graphically, so I have this, either I catch it or it drops, right? So it's success or failure. Now I'm going to ask you the question, if I do this 100 times, okay, so each of this is a success or failure trial. So binomial is basically how many times did I succeed. If the probability of success is P for each trial, binomial is how many times did I succeed. So over here we have n experiments. Okay. The second thing is that these are independent. It's important that they're independent, otherwise it doesn't work. Now in the case of juggling thing, of course, it's not independent, right? If I drink too much, then all the trials have lower probability of success. Also, if you get tired, you're going to have a higher probability of failure, so these are not independent trials. Okay, so independence is not assured. But in the case of binomial, we assume independence, and we'd like to know the number of successes. Okay, that's the value that we want to have. So x represents the number of successes, and it has two parameters, the n experiments and independent. I should probably say each succeeds with probability p. Okay, so the two parameters x, n, comma p, and it turns out we can represent this as the probability of the I successes is nothing more than n p. So n choose p, p to the I, n minus p to the power n minus I. So it's, I'm sorry, what? Oh, I'm sorry, yeah. Ni. I said I and I wrote p. What am I doing over here? 1 minus p. I say one thing and write another. Okay. So pi is n choose I, p to the I, 1 minus p to n minus I. What I really wanted to say was, if I use q, then it becomes easier to write it as p of I is n choose I, p to the I, q to the n minus I. And this, of course, are just the coefficients of p plus q to the power n. So if you take the binomial expansion of p plus q to the power n, the p plus q to the power n is nothing more than n choose 1, p to the n, q to the 0, plus n choose 2, p to the n minus 1, q to the, sorry, p to the, yeah, well, q to the 1, n choose n, p to the 0, q to the n. Or you can do the other way around. It doesn't really matter because the n choose 0. Yep, sorry, yeah. Yeah. So because these look like this, and these are the probability values, that's why it's called the binomial distribution. So in other words, what we're saying is that the probability density function for this discrete random variable chooses values such that the probability of I successes and therefore n minus I failures is basically given by n choose I. Okay, and so that's and sorry, n choose I, p to the I, q to the n minus I. That's the probability. Okay, so this, you know, so this is the relationship between binomial theorem over here and the binomial distribution. So it's just sort of the, in this case I'm just showing you sort of the formal relationship. There's a little bit more to it, but I'm not going to go into that. Let's just stick with this over here. P of I, I'm going to remove this thing here, so p to the I, q to the n minus I. So perhaps it's easier to look at an example of this. So let's take an example. We have a, let's say we have a LAN. There's a LAN segment which has these, let's say 10 stations on it, 10 Ethernet stations on it. So 1, 2, 3, 10. And I'm assuming that at any given moment in time, either any one of them can be active with probability 10%. So the workload is such that they all have a what we call a 10% duty cycle. Okay, so in other words, if I just go at a random moment in time and I look at it, probability is 1 in 10, 10% that it's active. Okay, so what I want to do is to compute what is the probability that that one station is active at any point in time, or 5 stations are active, or all 10 stations are active. I want to compute those probabilities. So we're going to assume that these network interface cards or stations are independent. We need to make that assumption. So the probability that any one station is active on its own is, we can think of it as being successful if it's active and unsuccessful if it's not active. Okay? So if it's, so we can think of this value p over here, each succeeds with probability p. We can think of this as, in this example, that p equals 0.1. Okay, what is n? Well, n is 10, we know that. Okay, so now we have all the parameters we need. We need to know n, we need to know p, and now we can answer any question about, we can answer about how many stations are active. We can just plug it over here. So let's take that for p1. The p of 1 is nothing more than 10, choose 1, 0.1 to the 1, and 0.9 to the 9. Okay? So, because 1 and then 10 minus 1 is 9, and this one turns out to be 0.38. Okay? So, the probability that one station, and exactly one station is active, that means not 2, not 3, but exactly 1, is 0.38, which is actually greater than any single one. Okay? It's sort of a counterintuitive thing, but not really if you think about it. So if I look at just this one, it's 10% chance of being active. This one is 10%. But at any moment in time, if I say, I don't care which one is active, just one should be active, obviously it has to be more than 0.1, and it turns out to be 0.38. Okay? What about 5? So P5, I'll just skip the math and just tell you the, okay, well, I should write it out, I guess. 10, 5, 0.1 to the 5, 0.9 to the 5. And this turns out to be 1.49 into 10 to the minus 3. So it's just pretty high that one of them is exactly one is active. Of 5 being active, it's 10 to the minus 3, and P10 turns out to be, I'll just give you the answer. It's 1 into 10 to the minus 10. Okay, 1 in 10 to the minus. Can somebody shut the door, please? So this is a really, really small number. I mean, this is 10 orders of magnitude, almost less than P1. And this single observation turns out to be behind a very, very large body of work on what's called statistical multiplexing gain. Now, what that says is that if I have a series, or if I have a bunch of people doing something and they're independent, okay, the probability that all of them are going to do it at the same time is very, very small. Okay, P10 is very small. It's 10 to the minus 10. So here is the application that people use. Let's say I'm building a hotel. All right, the hotel has 100 rooms. Okay, fine. I built the rooms. Now I need to give them phone service inside the room. Okay, so I'm going to put in phone service, and I have to pay for outside trunk line. Okay, outside trunk line is how many simultaneous calls I'm going to have to the outside. So if I choose the outside line to have only one simultaneous call allowed, then only one guest can make a phone call. And then the second person picks up the phone, it's busy. Okay, that's not good. The question is, how many phone lines should I provision? Okay, so it turns out that if we can think of the success in this experiment being the experiment being somebody makes a phone call, right? What we need to do is we can look at the fraction of time that a phone call is being made from a typical guest room in a hotel. All right? And we'll come up with some value of p. Let's say it's 0.05. So at any given moment of the day or night, it's 0.05. So typically what we do is we choose the busiest hour. We do busy hour planning. And based on statistics, we can find out that the busiest hour of the day in the hotel may be 8 p.m. Okay, so everybody came home from dinner, whatever they're going to call home. So 8 p.m. is the busiest hour. We look at the number of calls, and we'll find out the fraction of time, we find out the probability that a call is made, a long distance call is made from that hotel room. Once we do that, then we can plug it into this over here, because we can assume that the calls made by the hotel guests are actually independent of each other. There's no particular reason why they should be dependent on each other. And if you assume they're independent of each other, then we will be able to size the value of the n over here, that is the number of lines we're going to get, such that the probability that they're going to be used up is below any value that you want. Okay, so in this case, what I can do is I can basically say, look, if I have 10 stations, the probability that 5 are active is 10 to the minus 3. Okay, so if I size the line to be 5, capacity 5, then the 6th person coming on is going to have much lower, it's going to have less than 1 in 1,000 chance of actually using it. So there's a rough and ready analysis. To do the actual analysis is a bit more complicated. I've eliminated some details, but I'm giving you just this gut feeling. What's going on is that if each person is going to have a small chance of doing something, then we don't need to reserve capacity for everybody, because not everybody is going to be active at the same time. Okay, so in this case of this Ethernet segment, it's very, very unlikely everybody is going to be sending data at the same time. So even if I make the capacity less than what everybody else uses, it's okay. And this is what's called statistical multiplexing gain. It's actually called spatial statistical multiplexing gain. There's also temporal gain, which I won't go into. And we use it all the time, right? We have an Ethernet segment in the building, which is 1 gigabit per second, okay, or 100 megabit per second. And each of the network interface cards is actually 1 gigabit per second also. So if everybody is using 1 gigabit per second, of course we can't use it. Okay? It's going to be congested. But in fact, not everybody is using it at the same time, so everybody still gets reasonable amounts of gain. And this has a very strong economic incentive, right? We don't want to have too many people on and have too much load. So this turns out to be the case over here. Okay. Any questions about this over here? So the big issue here is that we're assuming independence, and we're assuming that everybody has the same probability. And if you look at what Rogers is doing in this whole network neutrality debate, what's happening is that we are having big users and small users. And the big users have a much higher P than the small users. That's what's going on. So the computations, which are based assuming everybody has the same P, are wrong. Okay? And the second problem is that we also have a correlation between people, right? If some movie becomes popular, everybody's trying to download it at the same time, which means that the independence goes away. And so the number of people that you get from this formula and the number of people that are actually there are often off by 1 or 2 orders of magnitude. So that makes it necessary in some cases to do traffic shaping. So these kinds of assumptions of independence and the same probability are just approximations, but at least they give us a good idea of what's the math behind statistical multiplexing gain. Okay. Any questions about this? Okay. I'm going to briefly motivate the Poisson, and I think I'm going to talk more about it next time. Let me at least tell you what the Poisson distribution is. So I'll just give you the... So Poisson is a discrete distribution again, and it has one parameter only, that's P, and the probability that X equals the value P, which is okay, so X equals I is Pi equals e to the minus P to the I by I factorial. Okay. So maybe I should call this probability because I'm using the word P too many times. The probability that X is equals to I, some value I, which is probability of I, e to the minus P, the parameter P to the I by I factorial. It looks a little bit kind of, where did we come with this from? And the reason why it takes this particular form, there are many, many reasons. When you study Poisson processes, we'll see that the Poisson process has this parameter. It comes up from a very fundamental mathematical basis. But for now, all I'm going to say here is that this parameter P for Poisson, the P in a Poisson, is actually nothing more than, or I should say, it's more or less the n for a binomial times P for the binomial. In other words, if we have, and this is true when n is large and P is small. So let's go back to this example over here. I have 10 stations, and each has a value of 0.1. So n times p is actually 1. It's pretty large. But let's say that n is 1 million. There are 1 million people who are trying to access some network, and the probability each of them is 1 in 10 million, something like that. So n times p is sort of small. N is then in that case we can replace the analysis over here, because if you have n is 1 million, p to the million, q to the p to the 1, n to the million, we don't need to do that. It's really complicated. We can replace this combinatorial analysis with the limiting values, which turn out to have this form over here. Okay, so it can be shown that the limiting value when you have n large and this value of p fairly small is the Poisson in this fashion. Okay, because you're just saying the limiting value of a combinatorial. It can be essentially approximated by this form over here. Okay, I probably should stop over here. So just to review what we did today, kind of started out with this notion of what a random variable is. I talked about discrete and continuous random variables and the notion of a distribution, mass distribution or a density function, and the expectation. And then we looked at Bernoulli and binomial. So next class I'll continue with the Poisson, and then we'll start with the continuous ones, which are Gaussian and exponential and power law. Okay.